Okay, now what I'll do in this session is that I'll talk the very preliminary stuff that you need to understand. I'm sure most of you understand in some way or the other, some part of it. Still, I would like to give a very brief overview about the basis set that you need in doing your electronic structure calculations. What you guys know as of now is the following, that you have a one particle Schrodinger equation or Kohn-Sam equation rather, and this effective potential that you know is composed of many things. You can nicely write it as V external R plus V hot 3 plus the exchange correlation. So these are the things taught you guys by several speakers, including Professor Manoj Varbala, and so yesterday Swapna must have talked about it. Now the question is that, as you know, that depending on the nature of this potential, right, you get different solution to the system. Now, all what we did is that we have created a second order differential equation, and to solve it we need a basis set. That's all. To solve the second order differential equation, how to generate a basis set so that the solution can be achieved. Now, what is basis set? The basis set in a very preliminary way can be defined as a set of or a collection of mathematical functions. Let's say that I have a given state like this. I want to generate it using certain mathematical functions, right? I may find it nice to use a set of functions like phi k equal to summation over k ck, or write x to the power 2k. This can create this. Okay? You take x, k is equal to 0, then this is basically a constant, you touch up in it. K is equal to 1, you get a parabola. Then k is equal to 2, you get different curves, right? So depending on the coefficient ck, you can find out some of these states together can form the black curve. Okay? So then we can say that this collection of this polynomial x to the power 2k forms the basis for this function. Okay? So that is the preliminary explanation. Now, how to design the basis for such a Kohn-Sam equation, or in general a second order differential equation? Well, it depends on several factors. So first factor here is the intuition that you want to use. In general, any set of orthonormalized basis set you can use, because you can make a transformation from one to other. But an intelligent guess will help you. What I will do is that throughout this next maybe 1 hour, I will provide how to derive that intelligent guess, which can be used as a basis set, used to form the basis set for this stuff. Okay? So for that, I will go to the very basic that we did in school or say college. In general, your Schrodinger equation, if you write and for an atom, then you have a spherically symmetric potential, assuming that the potential is offered by the nucleus, it's a positive charged entity, right? And for this, if you want to solve, right, This I are the quantum numbers. It can be your principal quantum number, orbital, angular momentum, and so on. Right? You can some of the other decouple this del square the Laplacian operator into two parts. Right? One the radial component and the other is the angular component. So if you look at it, you can nicely write out your del square as 1 by r square dou by dou r square dou by dou r, right? Plus 1 by r square sine square theta dou by dou theta sine theta dou by dou theta plus 1 by r square sine square theta dou square by dou. This is your Laplacian operator that you know. Now what you do is that you smartly decouple your psi into two components. That's a radial component, psi LR, and an angular spherical harmonics, YLM, that depends on the theta and phi component of it. Now, since your potential is spherically symmetric, right, YLM doesn't change with your potential. It's independent of it. Right? So then you make another radial equation which you intend to solve, keeping this out. Okay? Then the equation that you intend to solve is the following: 1 by 2r square d by dr, r square d by dr psi nl r plus L into L plus 1 over r square plus dr, right, psi nl r is equal to E nl r. Here I'll take a pause. So guys, if you look at the quantum numbers, the energy depends only on n and l. It doesn't depend on n. Right? It depends on the orbital angular momentum. L only. It doesn't depend on n. Right? That's the first thing. And you can rewrite this expression is a better differential equation by taking a new function which you call as phi nlr, that is nothing but, right, psi nl r into r. Okay? So if you do that, you get a new equation which is very familiar to you, phi nl r plus L into L plus 1. Like 2r square plus er minus E nl r. Now your net wave function, basically you can write out this component, or rather write say m or m, right? Which one?
Last term to go up.
Here?
This part must be this part. Otherwise, separation.
Once you do this first. Yeah. But what I would like to say that, have you ever looked at this wave functions? How do they look like? Or you say psi nlm. Have you ever looked at them? How do they look like? Okay. Here is a small picture that will help you to understand how the psi nlm vary. Right. I have taken the example of manganese. Right. So it has a 3d5-4s2 configuration. It will take the alpha 1. Right. Let me plot this wave functions. Right. And of course it has 1s2, 2s2, 3s2, 3p, 6, and so on and so forth. If I plot it, I see the following. my 1s, this is my R, this is my wave function, right? My 1s is very high near the origin and rapidly dies down. On the other hand, if I look at 2s, it's also varying and dying down, but it's died down little for a larger R compared to 1s. Similarly, if you keep on drawing this, then you have a 2s picture, and that's too big. Right? Your 3s goes, so this is 2s, your 3s goes something like that. Your 3p, and similarly your 4s. If you draw this plot, it's just basically 5 and R. Now, two things is clear from this. As we go from the
That's R square times radial or just the radial part of the wave function? The one which you have plotted, one is. It's R square
R
times.
square times this.
So that is
R square
R
times this.
square times the radial.
R square. Okay. So two things are very clear from this picture. The first thing is that your wave function is rapidly varying at the nucleus, at the origin. It slowly becomes smoother as you go away from it. The second thing is that your core states are more localized, right? So case 1, 2 observations that we make, that the wave functions are rapidly varying. Or rather say the origin. Second thing is that your core states are more localized, means their spread is limited, right? They're just around the nucleus, and your valence states are less localized. Their presence is very small near the nucleus, and the presence is more higher outside the nuclear body. This gives one intelligent guess how to construct the basis set for your Gaussian equation. Right? How is it? I can nicely split my space into two regions, right? Let's say my atomic sites are like this, random. I will nicely split, divide my space into, divide my space into two regions. One is called the core region. The second is called the interstitial region. Okay, so let me define a core region. Right? In this core region, I'll keep an eye on the rapidly varying component of the wave function. I'll assume that in this core region my potential is spherically symmetric, right? Then I will do a regular radial second order differential equation to solve and collect those states, multiplied of course by the spherical harmonics. And in the interstitial region, where my potential is relatively flat, not necessarily completely flat, it's relatively flat, I think I can design this area using certain plane waves. Okay? So, in that sense, or rather mathematically I will define this region into two parts. Your U R is equal to D R minus RC when R minus RC or R minus R rather. R is the atomic size, it's less than the some cutoff radius RC, okay? Then it's equal to some flat to constant kind of stuff when it is in the interstitial. Right? So I will generate a set of, so in this region, obviously I will solve the second order differential equation 2m del square, let's say phi ke r plus b r minus r phi ke equal to e phi ke r, right, for the core region, or the sphere that I have designed, which people call Morgan sphere, okay, and phi k r is equal to e to the power I k dot r in the interstitial. Now, you must be wondering how this k came to into the picture. The spherical symmetric solution, there is no rule of use of k. Now, just imagine that in this, at this boundary, my solution due to the core potential, that is VR minus capital R, and the plane wave, this should match. There's a boundary condition. At this boundary, this should match. Okay? Professor G.P. Das will talk much about it later, right? But what I'm saying is that if they match, since my plane waves will be defined in the interstitial and they have a k component, right? That k component will bring the dependence to my phi k. Okay? So that you keep a note of it. Now, this is the basic of all the augmented plane wave mechanisms, what you call APW. So all APW are starting with this idea. Now I'll talk another way to design the basis. Okay? That way is the following, what we call OPW. That is orthogonalized plane wave. Yes. one thing here I forgot to let you know that a single e to the power ik dot r will not solve the crystal Schrodinger equation. Okay, a single e to the power ik dot r will not solve the solution of the will not solve the crystal Schrodinger equation. Rather, if you have done for the basic honest matter 1, you define a new wave function which is the expansion of this some coefficient Ckg e to the power I kg r, where your k lies in the first Brillouin zone. Okay, this will solve the crystal Schrodinger equation. So instead of a single plane wave, you need a bunch of plane waves, each associated with a reciprocal vector g and has a crystal momentum k. Those bunch of plane waves augmented with the radial component of the wave function together will form the basis, right? Now, a similar idea that is coming up in orthogonalized plane wave, just that we are not going to solve the radial equation inside the Marpentine sphere or in the core region. Okay? Rather, we'll take the help of already existing or already established the core orbitals. Okay? Let's say that we have the know-how core orbitals. What do I mean by that? If you recall the functions that I plot few minutes back, I plotted for 1s for the example that I gave. I plotted for 2s, 3p, 3s, 4s, 4p, not 4p, 3d. What I noticed there was that my 1s is very, very localized. It has no presence in principle outside a cutoff radius RC, which you conveniently choose. So also 2s and 2p. Right? What you do, you split all the electron states or the set of electrons into two groups. One is the core electrons, or the group consists of core electrons. The other group consists of the valence electrons. Okay? So the valence electrons, you want to find the basis that represents the valence electron, right? Now let's say that I know the core orbital. For example, I know my psi 1s, psi 2s, psi 3s, so on and so forth. It's associated with certain orbital angular momentum, of course. Then what rather I will do that? I'll say that my OPW applicable for my valence wave functions can be defined as e to the power I k dot r. That is of course the solution in the interstitial plus a linear combination of all the available or all the known core orbital, say psi k. These are my localized orbital. But then I impose a condition, because this wave function has to be orthogonal to the core states in the core region, right, in the Marpentine sphere. Okay? Therefore, I have to put the orthogonal condition which is nothing but you take in a space dqr psi kc star r phi kr. If you impose this orthogonal condition, then what you get in return is the following. You get the value of the coefficient bc which is nothing but dqr psi k c r e to the power I k r. Okay, so this is stands for the core states that you have to know how. Okay. So if you recall, I am no more solving this second order differential equation inside the sphere, inside the sphere of cutoff radius RC. Rather, I am trying to find a collective set of functions, the collection of the core wave functions which are together representing my total wave function for balance. Okay? Then further you go ahead, like you have expanded in a PW case. In LAPW case also you can extend psi k as summation of G, CG, phi k plus G. This is the expansion of each phi k, right, in the crystalline system. This is how you can construct the orthogonalized plane wave. I'm sure Professor Saurabh must have talked a bit more about it. Okay. Now let's see that if I want to associate each of them, I want to associate each of them with certain angular momentums, the quantum numbers L and M. I can happily design my balance wave functions as let's say phi d Lm, right? These are the valence wave functions associated with certain angular momentum quantum numbers L and M, which is equal to psi Lm, or rather phi L d R. Now I will collect all the core states associated with same angular momentum L and M. Therefore, I will write it as summation over T D L M psi C L M. Okay, all the core states. Okay, so I will happily collect all the core states associated with same angular momentum L and M. In that way, I can generate this net wave function, which is valid throughout the space. Okay. If I interpret this expansion, right, the expansion in this space, rather than summation, I can go ahead and do the integration. You'll see that I can rewrite it. Of course, I'm not deriving. I can rewrite my phi Lm dr as dqk clm, some coefficients like this, k phi k dr, and phi, sorry, e to the power I k dot r, because if you look at it, this component more or less contribute to the first component of the wave function. Then I can write phi Lm in general dr is equal to dk clm k phi dkr, and the coefficients bl and c, right? So bl and c can be realized as dqp clm. So these are the expansion coefficients like this. Psi k clm, okay, Now you'll find that this is a very smooth function. Defining the wave functions outside the sphere, or the sphere with some sort of radius RC. Okay, this contributes morely in the inside or within the sphere. Okay. Now I would like to draw a particular 3s valence states and see how the smooth state look like. Okay. Let's say that my real 3s states, if you recall the plot that I put, is the following. This is a real 3s state, typical. So rapidly varying inside the core region and smoothing out outside. Okay. 3s state. Now, if you try to plot the smoother one, there is no unique way of making the smoother one. You can find many. Couple of them you can draw like the following. Or you can defining the sort of RC. This. You are really not worried about, in principle, the behavior of the wave function near the nucleus. You are rather worried about the behavior of the wave function far away from the nucleus. Okay? And that is where the idea of pseudo-potential method kind of emerges. So they say that if I know that this, if I do the whole Schrodinger equation for the total wave function phi ln I will get some ED ln phi ln B. I know that. But if I can find out an Hamiltonian operator, right? Let's say H tilde, which acts on the smooth component of the wave function phi ln tilde B, or is equal to E ln B phi ln B tilde R, then it solved my purpose. I am going to use this particular a new operator, Hamiltonian operator, a new operator rather, and not Hamiltonian, which operates not inside the core region, right? It acts on my smooth part of the wave function. It will give me the same eigenvalue that I was expecting from my real, the all wave function. Okay? Now, this idea has been created, I think, the present chairman is an expert in it, so I need not dwell much on it, right? So this idea first given by Philip Antonic, so which you can write as H, particularly they write it EKA. So that is nothing but minus half del square plus V, that is a regular effective potential, in addition to a non-local operator. Okay. Now it so happens, or if you derive it or go ahead and look at it, you will find that this is a repulsive. If you do the derivation and check it out, this VR is a repulsive. right? So therefore, the diverging potential that is responsible for this rapidly varying wave function, the wiggles of the wave function, right, can be replaced with a new potential which you call as a pseudo potential. There are many versions of pseudo potential, which I am not going to pursue. But what I mean to say is that the OPW, this orthogonalized plane wave mechanism, right, construe the real basis or the very appropriate basis for the pseudo potential method, those who are using. Okay. So now, having discussed all this, then you must have heard about what you call as the PAW, projected augmented method, or ultrasoft, right? So in PAW and ultrasoft, they don't ignore this zone completely. Rather, they add on some auxiliary wave functions, which is appropriate inside the cutoff radius, inside the sphere, right? So, and that way they form the PAW and the ultrasoft basis sets. Okay. Then there are many other things. Professor G.P. Das will go ahead and talk about it. What you call as the linearization of the basis, right? So I'll just write one line and leave it to Professor Das. Right? You can create a set of bases which you call the linearized basis. Right? So in the linearized basis, what you do is that you take the, let's say, phi linear. You take the plane wave component as it is for outside the sphere, right? But inside the sphere, right, it will have a set of the combination of the wave function that will define inside the sphere as well as its first derivative. Okay? I'm not going to discuss why the first derivative, how it helps, and what of that. But this is the another way of presenting or constructing the basis sets. Okay? So those who are doing this LAPW method, they particularly use the linearized augmented plane wave method. The linearization happens in the core region, and the earlier days people used to do the linearized Markantine orbital method or LMQ method, where they linearize the Markantine orbitals. Okay. Now, so far what I have talked about creating a basis that is so universal. It defines in my throughout the space, categorized into two parts, a zone where my potential is kind of flat, and zone where my potential is kind of diverging. The wave functions are rapidly varying. Now, can I go back and see if I can create localized orbitals as part of my basis? Okay? Those who are doing the quantum chemistry or clusters, more or less they use the localized orbital like Gaussians, right? So now I will highlight a little bit on the localized orbital. So that idea, I will rather say how it evolves, okay? Let's say I have a closed cell system. write your rareness. Right? If I have a closed system, all the states are occupied. Right? Assume that all the states are occupied, then your charge density NR, so that is nothing but all occupied 2L plus 1 psi NLR square. Okay, or you can write it as summation over NL occupied 2L plus 1 phi NLR square. Okay? Why this 2L plus 1 came into the picture? If you recall my discussion, your energy depends on L. Right? Your energy doesn't depend on M. Right? So if L defines, then you have 2L plus 1 degenerate states. All states are occupied. That's how you can construct your charges. Now, for your effective potential, which consisted of external plus B hot free plus VXC, keeping aside this external potential, which is kind of generated ion, right? These two are depending on the density NR. Now, if you look at this expression, right, you see that your NR itself is spherical symmetry. It doesn't depend on the different alpha. Therefore, your V effective R is spherically symmetric. Then you can go ahead and solve the radial Schrodinger equation to obtain all the bounds. Okay, this is true for all closed cell systems. But when all the angular momentum states are not completely occupied, then this is no longer true. If this is no longer true, your NR is not spherically symmetric. If your NR is not spherically symmetric, you cannot say that these two components are spherically symmetric. If these two components are not spherically symmetric, you cannot get this bound states whatsoever, and that's why you follow those APW, OPW, all linearization and this and that. Now timing, assume that even if they are not spherical symmetric, I can make an approximation in my mind saying that my states or my orbitals or my bases are kind of atomic like. Okay? So assume that your basis functions are localized, or say they resembles the atomic like orbitals. Okay? Now, you construct a basis set out of this kind of orbitals and you say that localized basis. It's true that they never represent the real, the eigenstate of a system, but they are very, 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 very useful in creating an intuitive picture to understand the basic physics mechanism, and that has been used as a set of linear combination of atomic orbitals. That lead to a tight binding method. Here you assume that yes, my basis sets are localized, they're atomic like. They interact with the nearby ones. They really don't interact with the ones that are far away. If they interact with my nearby one, like if you recall your chemical bonding, right? Whatever the effects in the system or whatever the properties that you see in the system are due to their interaction in the nearby and nearest neighborhood. Okay? So I'll dwell a little bit more on this atomic-like orbitals and give a brief glimpse how this tight binding model helps you in understanding certain physical phenomena, right? And for that purpose, I may love to redefine my potential a little bit. If you take an isolated atom, your potential goes something like that. This is the atom center. It dilutes at the nucleus and away. Now you bring a collective collection of atoms, such atoms, right? The potential superimpose with each other, and you create a net potential U, which is nothing but summation over U atomic R minus R, where R is the capital R is the atomic size. Now this U is, if it's a crystalline system, it is periodic. Okay. Now what I'll do is that I'll take my atomic-like orbitals as the basis. Okay? So let's take okay? But you know that if it's a crystalline system, I have to create a trial wave function which has to satisfy my what? Blocks condition. Okay? So right, so these atomic like orbitals, they satisfy 2m plus u atomic. Okay. Now this are the orbital, the atomic like functions I am taking as my basis set. This U atomic, as if when the only one atom was there, every rest of the place is empty. Okay. Very good. This you can borrow from your closed cell approach and get the atomic like orbitals. There are no issues about it. Okay. Now, let's define a wave function which cater to the periodic potential U and satisfy the Bloch's condition. That is nothing but some normalization constant. You see that n is the number of unit cell that you are considered. Let's say normalization constant R e to the power I k dot R psi n atomic R. This n is the state represents the state with energy eigenvalue En. Okay. I give you a small exercise with you guys. Prove that satisfies the Bloch space. First it is N K. Okay. Go ahead and check it at home that it satisfies the Bloch condition. Okay. Now this is created corresponding to the state with energy, atomic energy eigenvalues En, right? As you know that there are many atomic energy eigenvalues, n goes for large numbers, right? So then I have to create the most general. Let's big a big psi MKR as the linear combination of this psi MKR. Okay, so I created one psi MKR which satisfies the Bloch condition, right? Corresponding to the atomic eigenstate psi n atomic. Okay, then now I created the most generalized wave function out of this, out of atomic like this. It's a localized basis. Now if I create that, right, I can go ahead and find the extrema of the following equations psi n k r H crystal. So that is your H crystal is nothing but L square plus summation over R or plus U, this U, yeah. This crystalline, where U is the total potential in the system, which is periodic. All right. Psi n k r minus ELM or EM, rather psi n k r. Find the extrema of the above. How do you find that? You apply the variational principle as you have learned. Which are the variable parameters? Actually, your variable parameters are your coefficients of linear exponents. Because you know that this is fixed, this we cannot alter with it. It is enveloped with a plane wave component, or else it write it in R. Okay? Therefore, the only one that you can vary is the CMN. You keep on varying, okay? And get the extrema of it, and that will give you this Lagrangian parameter EM as your the solution to your system. Okay? Is there any question at this stage? I would like to take a few questions.
You should ask.
Good. Now,
Do you want to take a 5-minute break or do you want to go take for 55 minutes or more?
okay, as you wish.
Maybe
Okay, so we'll take 5 minutes break, we'll come back and discuss the rest. Cutoff radius in which the potential assumed to be rapidly varying, negative, and rest where it is smooth or flat. Now what happens if you take a crystal with heteroatoms, different set of atoms? Is it going to affect the construction of the basis set that I talked in the context of plane wave method, right? It is not going to affect, because at the end of the day, you are creating a, let's say there are two different atoms, atom A and atom B, right? Its cutoff radius is something, let's say RCA, its cutoff radius is something called RCB. So RCA and RCB, right? Now, between them there is huge amount of interstitial region, right? So if my plane waves are e to the power ik dot r, some expansion of it. So here when the plane wave, the wave functions is this component, it borrows the rapidly varying wave function inside this atomic region. When it sees the wave function in this range, in this the radio sphere, then it borrows the rapidly wave function from here, right? For example, when you make the OPW basis set, right? So in this component, it will be basically the core states of atom A. In this component, this will be core states of atom B. So it's very universal. Okay, so there is no issue with that. Okay, so now let's get back to the tight binding model. Okay, so let's see. Now, if I find the extrema of this, the expression that is, it's basically a Hamiltonian matrix and a overlap matrix. So you can write it as a HMM, and this is SMM. In general, MM prime, right? And then you find the extrema through variational principle, I mean by varying the CMN or the coefficients and get the EM for the best possible value. Okay. Now, if you do that, right, at the end of the day, you are basically calculating two factors. Let's say that you are successful in doing this variation, then you end up with an expression of the following set: n prime C m n prime h, right? So n prime minus e n s n n prime, okay, is equal to 0, where h n n prime is in terms of this psi nk. To recall, the psi nk we built out of the atomic orbital psi n atomic r h crystal psi n prime k. Okay. Similarly, s n n prime psi n k r. Right. And corresponding to the eigenstate, eigenvalue En. So this is my eigenvalue. Okay. Now this presents a beautiful picture. If I have taken my atomic orbitals, then my atomic orbital, they have some symmetry depending on L and M. So I am involving one symmetry of the atomic orbital. Okay. Now that's not all. Also symmetry of my crystal. that I'm working. Okay? Those together define this matrix elements, right? For visualization, let's look at it like that. If you have an s orbital, right, atomic like s, let's say s orbital, that from where you have constituted your psi nkr, right? Another s orbital corresponding to the other atom, right? Let's say psi s. This is r minus r. This is r minus r prime. Okay, and you are examining their interaction, right? So what you will see is the following. If those two are lying along the x-axis, if those two are lying along the y-axis, or some other axis, or some other axis, you will say that the interaction is isotropic. Your S electron cloud is spherical symmetric, so their interaction is isotropic. But on the other hand, let's say the p orbital take into picture. You have px, py, pg. So if I have a px orbital, right, and I bring another px orbital along the x-axis, okay, or let me be careful about it. Okay, you see that their overlap is of one kind, right, which in chemistry you call sigma bonding. But at the same time, you take this px orbital, but the other atom lying along the y-axis. Okay, so their overlap is weak, and hence their interaction will also be weak. It's sometimes called finite. Okay. Now, interestingly, if you put the crystal symmetry into picture, right, not necessarily that your atoms will lie along X or lie along Y, they can lie anywhere in the space. Therefore, you can have a picture of this. It's neither along X nor along Y. Then these two will have a component of some B sigma, some B theta. Okay. So what you are basically doing is that your physical intuitive picture through symmetry are bringing back to this evaluation of this matrix element, and then create a physical description of the system. Okay. Of course, we should not stop there. There are much more to the tight binding model. And some of the derivations I am going to write. Your EM, some interaction, right, equal to, or rather say that your E, I am not assigning any quantum number per se, I will come back to it. Your E will have some atomic component, I mean this eigenvalue is there, plus it will have some perturbation. This perturbation due to this chemical bonding and overlap of the states. Okay, so I will give a generalized picture. Your since you can take a monoatomic system, diatomic system, heteroatomic, large number of atoms in the basis. A generalized picture will be basically SI, HMM will be E M delta M as that depends atomic, plus some non-K dependent term right? It's not of much interest to us. Plus summation over delta, I tell you what is the delta, e to the power I k dot delta p n. Okay, but it means that suppose let's take a typical two-dimensional lattice. Okay, I have an atom sitting here. I have an atom sitting here. Let's say for simplification. I will prefer to study the interaction in the nearest neighborhood picture. I mean, I'll say that this interaction is direct or strong enough. This interaction may not be strong enough. Weak. Can be neglected. Okay, so I restrict. Then I know that if you do this, actually this is a term which is come as e to the I k r minus r prime. So let's say this side position is r, this side position is r prime. It's e to the power I k dot delta is basically e to the power I k r minus r prime. The difference. This is the phase factor that you are to the system. Okay. Now what is TMN? TMN is basically the interaction between atomic orbitals M and N. It can be SS, it can be SP, it can be PP, that could be PHPX or PHPY, or PHPZ and so on. Okay. Now, this is nicely evaluated by Slater-Koster. If you browse the book, okay, you'll find that Slater-Koster interatomic matrix element or something. By binding matrix element. I'll just cite few of them. This two-center integration, Jupiter was asking me to if I can teach, but probably that will take a little longer. So your Slater-Koster interaction element, you can define as SS is equal to ESS sigma, because it's isotropic. S is isotropic. Any direction you put an atom, the interaction is M. Now EHSX, that is LESP sigma. I'm putting just S and P orbital. If you go to the book, they have D orbital, and now they have F orbital, and so on and so forth. What is this L? So Slater-Koster, they took care of the crystal symmetry in this picture. Okay? Let's say that, right? I want to study the interaction between the s orbital and x orbital, right? So this is my s, this is my x. Okay, so interaction suggests that only along the x-axis, because your L is equal to 1, M is equal to 0, M is equal to 0, so minus. Okay? So if I have a state like this, their interaction is weak. So because your M is equal to 1, L is equal to 0, M is equal to 0. Okay? Similarly, if you study the EXX, okay, who can tell me what will be HSY? I defined HSX as LBSP sigma, L being a direction cosine. The direction cosine basically represents the position of the second atom with respect to the first atom in this term. So then your HSY will be nicely the STC, STC. If your n is equal to 1, of course it's a full sigma interaction, right? Your n can vary from 0 to 1, by the way. Okay? The diamond-like structure, you don't have n is equal to 1. Okay? It can vary from 0 to 1, right? If n is equal to 0, then that interaction doesn't exist. Okay? Similarly, two more terms I'll write, then we'll escape. Then we'll do a small example, which you'll realize why it is so important. Your EXX, you'll see that L square be PP sigma plus 1 minus L square be PP bar. A little while before, I was just talking about this. I said that if I have two px orbitals are lying along this, it's a purely sigma interaction. Your L is equal to 1, therefore 1 minus L square is equal to 0, hence BP pi contribution goes 0. The vanishes. Okay. But on the other hand, if I take something like this, your L is not necessarily 1. Right? It can be 0.5 or whatever it is. Then, yes, let's say if it is 0.5, then you basically get 0.25 dP sigma plus 0.75 dP bar. Your contributions are basically coming from 75% from dP pi and 25% from sigma interaction. Okay. Now, having said this, who will find these parameters? These parameters are nothing but your tight binding interaction, that PMN that I was talking about. How will you find? This is the drawback of this consideration, because I am not doing any self-consistent calculations. I am not subjecting it to a the Cohen-Sum equation using this atomic-like orbital as basis and allowing it to go through the self-consistent method that we have learned.
I have a question. Shouldn't HSY be 0?
No, it's n as q.
No, because there's a positive orbital and a negative orbital, and then the.
This is S step.
Can you just draw what?
So this one is something like this.
Yeah. Yeah. So you will have an integral with the positive lobe and the negative lobe, and won't they cancel?
Which one? Okay, let me draw this picture. Maybe you are right. Make it a clear picture. Let's say this is my S orbital.
Yeah.
So I'll put a P orbital. Let's define the positive and negative lobe as we wish.
No, there that comes same as your HSX. It's you've just rotated it. But
Yeah, exactly. That's what I'm saying.
No, but you were saying if it's here.
Yeah.
If it's there, it's fine. But if it is here, this here.
Zero.
Yeah.
It won't return.
Yeah.
Yeah, it won't return.
Yeah.
Yes, that's fine.
So
this is
So which one are you calling HSY?
this one.
Okay.
This one is HS1. This will be 0. For example, the way we designed your SX.
So what is your notation? Can you just explain your notation then?
So my notation is basically, let's say, PSX, that is the interaction between the S orbital and the PX orbital.
But how are they in space with respect to each other? That also matters, no? So where do you get that information?
Oh, that information was inbuilt at which what I call as the Slater-Koster interactions, right? Which I am not
In your
discussing.
notation, it
Uh-huh.
matters how they are oriented with I mean, whether the orbital is on this side or this side, right?
Mhm.
So your notation doesn't.
So
give
you
that
take your,
information.
yeah, that's nice question. Let's say that, let's draw a picture. Let's put two kind of atoms, right? Define this x-axis, define this y-axis. Now I would like to invite the question that you have.
No, so if you have an s orbital and an x orbital.
If I have an s orbital and x orbital, but between two, either this row or this row, right?
No, you know, yeah. So it matters also whether if the s orbital is here and the x orbital is here, it matters whether it's here or here, right?
No, that is defined by this L, M, and N. That's the direction cosines. This direction cosines will take care of that orientation. That's why I was saying that that will come to the Little method, right? So, for example, here I will say L is equal to 1, M is equal to 0, N is equal to 0. Here N is equal to 1, L is equal to 0, N is equal to 0. Therefore, if I say that my HSX is equal to L VSP sigma, something like that, right? Obviously, that
Can you
when I
just
refer
explain
to,
what is L and N?
so these are the direction cosines that you calculate, simpler, right? So when I say that LVSP sigma, right, then I can see that this s orbital and this px orbital, they don't interact.
That's what
Yeah. So I mean, it is very clear from
Yes,
here.
defined it. Can you just define L and N?
So so you take that x minus x naught. So L, if I'm clear, then you say that the whole distance d. So m is equal to similarly
For Y.
for y minus y. So I mean, you can see that your L is equal to 0. Therefore, HSX becomes this atom and this atom will be vanished. That's the beauty of this Slater-Koster method. Okay? Basically interacting elements. I don't know their values. What we do in this method is that we'll go back and relook at the already available or the existing all-electron structure or all-electron band structure or certain experimental data. We fit our interaction with all this tight binding Hamiltonians with that the other level experimental data and optimize these parameters, then give a physical picture. Okay? To explain that, we'll touch upon graphene little bit. Okay? Which is, I think everybody understands. Okay? So, graphene, as you know, is a 2D lattice of this shape. Okay. Now, this is one translation vector say P1. This is other translation vector say P2. Right. I have atoms of nature A. Right. So, due to unique valency, I will define these atoms as B. Let's say 2 sublattice in the system. Then there's A sublattice and B sublattice. I want to study the interaction between the A and B. If you go to a full band structure of graphene, then so this is your K part. You define the K part. Favorably, people define gamma Km, K being the direct point, right? You have a Px, Py, S dominated spectrum. But your formula lies here. Okay, and the linear Dirac bands appear at this point. Far below the band that you see are actually the planar dominated by the planar orbital pH and py as due to the sp2 hybridized states. But we see that the formulable or the properties of graphene actually defined by this linearized bands. I mean the linear Dirac space. Okay. Then out of my curiosity, I am less interested in studying the bonding of these states. Because all my properties I am extracting apparently from here, until unless you study some defect states like magnetism or stuff. A general electronic picture at the formulable is well defined by examining these states. Okay? You will find that these states are PG dominated. Okay? Then I will just work on my PG-PG interaction. And if I can reproduce this picture, then I have understood the physical mechanism behind formation of this. Alright? Okay. So now I have two sublattice A and B. Then I am creating actually a Hamiltonian matrix of this nature. HAA, HAB, HBA, HB. When I say AA, means PG orbitals of A interacting with the PG orbitals of other A's, right? And BB means PG orbitals of B also interacting with other PG orbitals of other B atoms. HAB means PG orbitals of A interacting with the nearest neighbor PG orbitals of B, and so on and so forth. Okay? Time being that, assume that this distance is far enough. So this interaction is weak. You can just say that is the freedom that you get in Slater-Koster approach, right? You say that it is some no interaction, so let's define U1 atomic kind of EPG atomic. No interaction. No K dependent terms. This is absent. So we'll leave it. And similarly, since there are two same carbon atoms involved in the system, this is also EPG atom. Okay? And these are constant numbers. They don't vary in the K space. Since they don't vary in the K space, you can conveniently take them as a reference 0. Now what left is your interaction HA. Right? If you recall my expression, it's in general write HMM, that is some delta factor, MM, plus some e to the power ik dot delta, then some PMM. Okay? So if I examine this, since these are two other atoms involved in the system, this first component analysis, delta M is equal to M not equal to N. So then I just left with e to the power ik dot delta, summation over delta. T is the interaction strength between this state nearest neighbor interaction. Since they are same carbon atom, the interaction is same, identical for all. The moment you jump for a heteroatomic system, this T values also vary. Okay? T, and that's all. Okay? Now you identify your delta. Right? You can go ahead and check it. Let's say my A is sitting at 0, 0, 0, that is your choice. You can find the positions of B. Right? So this position, let's say some, I believe it is A by root 2. A is the lattice parameter, right? So first, there are three B1 B atoms. So one stays at, let's say this one. So it is 0 minus A by root 2, 0. Of course, this is immaterial, it's a 2D lattice. Okay, then your B2, so let's say this is my B1, this is B2, this is B3. So B2 will have it, so this is roughly a by 2 minus a by 2. Then this distance is, I forgot, probably a by root 2 plus a by root 2. And this is plus a by 2. Something, check it, I might have done some error, doesn't matter. If you find out, then you can evaluate your delta, right? Then your summation is basically e to the power I k dot delta 1 t common plus e to the power I k dot delta 2 plus e to the power I k delta 1 corresponding to this r minus r prime, delta 2 corresponding to this r minus r prime, delta 3 corresponding to this r minus r. Okay, now this is a k dependent terms fk. Okay, therefore I can replace it as a pfk, the function of k, and say Hermitian matrix, I'll be happily writing as ph dot k. Right? So if you diagonalize it, obviously you will get lambda square, lambda is equal to plus or minus t of f star. Yeah. F star. Okay? The plus component is your conduction band. The minus component is your valence band. And they touch exactly each other at a certain k point. It so happens in graphene, right? They touch exactly each other at certain k points, and that's the point where the Dirac cone is formed. Okay, and if you fit this expression with the all electron band structure picture, or if somebody has got by some means of experimental study, then you will find roughly that your P is something like 2.6 to 2.8. Okay. Then you say that these states do interact with each other with certain interaction energy. Okay. And it has been identified that if you go from first neighbor to second neighbor, the interaction energy is hardly 0.2 electron volt. It gives you the physical picture. Yes, my interaction is very strong at the nearest neighbor level and vanishes as I move forward. Okay. Also, if you do a full-fledged study, go to second or third or fourth, then you will see that no matter what the interaction of second or third or fourth neighbor in the stuff, your linearization at this point and touching of the bands at this point doesn't go away. Then you tend to tell that, yes, I understood the physical interaction mechanism in the system. The Dirac behavior appears just because of the nearest neighborhood interaction. So this kind of physical descriptions or the mechanism, you can extract this simple type binding models. Okay? Now, people have not stopped at this simple type binding models. Of course, they have used the localized orbital as a basis set to the Cohen equation. Though Professor Dilip Panara was saying that most of the chemists use the Gaussian as the basis set for Cohen equation for clusters. They calculate in chemistry. I'll just touch upon the Gaussian basis set. Then I'll briefly talk about the Slater-type orbital as the two other the basis set. Then we'll stop there. Then I will invite some questions. Okay? We know that any Gaussian orbital can be written as some prefactor, some normalization factor, let's say beta, into e minus some spread alpha aspect. Okay. Now I have the option of varying this prefactor and this prefactor to create many such Gaussian orbitals. Okay. Why Gaussian orbitals? They're easy to integrate. Analytical solutions are possible. If you make a product of two Gaussian orbitals, that will give an third Gaussian orbital, right? If you differentiate a Gaussian orbital, it will give a polynomial multiplied with a Gaussian orbital. So these are the beauty part of the Gaussian orbital, right? And also it's varies, so rapidly decreases. The spread is limited. Okay, you can define the localization as you wish for the spread parameter out. So in a sense, they are the real localized states. Okay, few Gaussian orbitals I have written down for your information. In general, of course, the Gaussian orbitals people do write like this, the following Gaussian type orbitals. So they write G, alpha, L, M, and N, X, Y, G. So that is equal to N e to the power alpha F R square X to the power L, Y to the power N, Z to the power N. Okay? So this is the spread. These are the polynomial components, right? If your L is equal to 0, M is equal to 0, N is equal to 0, your spread is like S type. If your L is equal to 1, M is equal to 0, N is equal to 0, your spread is X type. Similarly, you can create a Y type or Z type orbital as the system, which resembles, I am not saying exactly, which resembles your atomic orbital S, P, X, P, Y, P. Okay, so you kind of tend to form the atomic type orbital from the Gaussian expression of this form. Then there are certain drawbacks with it. What are the drawbacks? Look at the slope at this point. Slope is 0. Okay? If you recall your hydrogen atom problem, actually your wave functions varies with R at some time. It doesn't vary with R square. Okay? So the real localized orbitals, they decay rapidly compared to your Gaussian orbitals. Okay, so these are the main two disadvantages of it. Then Slater came into picture. He find out something called Slater-type orbitals. Okay. What he did is that he took a set of Gaussian orbitals and made a combination of them. Right. See, is it easy to form a S-type orbital or a PX-type orbital or a PY-type orbital or PZ? Difficult to form D and F orbitals. So Slater took all of them and created a new set of orbitals. Few of them I can give the example. You can take GXY, that will resemble like your DXY. You take XY means L is equal to 1, M is equal to 1. Similarly, you take GXZ, that gives you DXZ, resembles GYZ, that gives you DYZ. On the other hand, if you want to produce a DG square, I mean 3G square minus R square orbital, then you cannot rely on one or the other. Rather, what you do is the following. You take 1 by 2 of 2GG minus GXX minus GY. That will resemble the DG square orbital. Okay? Similarly, if you want to produce DX square minus Y square, then it is something like root 3 by 4 gxx minus gyy dx is plus. So on you can produce the f orbital and so on. Now you take these as the basis set, inject to your Gaussian equation, right? And get the solution. Okay, then there are many other basis set, numerical basis and some other stuff which I am not touching upon. If I summarize the lecture so far, what we discussed that we first got the intelligent guess by dividing the space into two parts. One is the interstitial, other is the core. We realized that in the core part, your localized the rapidly varying wave function can be a solution of your second order differential equation, radial equation that you see, corresponding to a spherical symmetry. Potential, in the interstitial region, it is easy to augment it to plane waves. Okay. Then of course you do a boundary matching and all the conditions has to be satisfied. Then in the second step we moved on. We stopped ourselves to the plane wave with the interstitial, but in the core region, rather we said that instead of solving the Schrodinger equation, rather we get that a combination of already existing core orbital contributing to my wave function. That's what we call orthogonalized plane wave method. And I told you very briefly that this OPW is the basis on which your pseudo potential method has been examined. Basically, you are overriding the wiggling that you see near the nucleus, to smoothen the potential, smoothen the valence wave function. For the same energy eigenvalue, valence eigenvalue, right? You are only working on the interstitial part. Then I briefly touched upon the PAW, that's the projected augmented method, or the ultra soft. I have not gone through the details. Then I also told you that for various reasons, they don't stick to this APW or OPW or something. They do the linearization of the basis, right? From there, your LAPW or LMPO emerge. I believe Professor G.P. Das will throw more light on that. Then we took a back seat. We looked at a closed cell approach. We assume as if we are creating the atomic-like orbitals for the system, right? And you are examining the interaction of them in their neighborhood, in their periphery. From there, we develop a type binding model, right? So basically formed based on LCAO, linear combination of atomic orbitals. And we saw that how a physical description can be emerged from this type binding model. Graphene was the example that was given. Then again moved on and created the localized basis set again as a combination of atomic-like orbitals using Gaussian as a basis. And we subjected that to the Gaussian equations, how that can consistently get your result. And examine the disadvantages of the Gaussian, then fixed it with the Slater-type orbitals. Of course, many other stuff I have not touched upon, like what is the numerical basis and others. Others will